Hello, everyone. Can you hear me? Hello, am I audible?
Yes, sir.
Yeah. So wait for a few more minutes since like restaurants here. We'll wait for 5 minutes and then we'll start the session. Okay? So wait for 5 minutes and then we'll wait. Okay, so we'll begin now. Okay. I think there are enough people. Let me share my screen and okay, before I share my screen, in this session we'll discuss week 5 concepts. Okay, week 5 and week 8. Okay, so the week 6 and week 7 those will be discussed by Vishal sir. Okay, and that will be discussed in the next session. So this session will primarily focus on week 5 and week 8. Okay. Just give me a minute. I'll share my screen. Are you able to see the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so let me connect my writing board too. Okay, give me a minute. Okay, so let's begin now. And we discuss mock test problem, test problem. Okay, we'll discuss. Problem 1, 2, 3, right? Okay, so we have this decomposition for the matrix. Okay, is Qt to transpose if S is multiplied by constant K, then the respective decomposition will be okay. First things, what do we know here? We know that the matrix Q, right? Q is what? Q is orthogonal, right? We will try to provide the mock test solutions in detail. Yeah. Okay. So Q is going to be orthogonal, right? And then Q star is also going to be unit orthogonal matrix, right? I mean, where each vector, or each column, right? In that particular matrix, it is a unit vector. So Q1, Q star, they are not going to change, right? The only thing that's going to change is T. And what's going to be the T? T is going to contain the diagonal. I mean, eigenvalues, right? Am I right? Eigenvalues of S generally. You're multiplying by constant K, right? So when you multiply S by a constant K, right? Then what's going to happen to the eigenvalues? The eigenvalues are also going to get multiplied by that value, right? So the matrix T, it's going to get multiplied by K. Okay, so that's what is going to happen. All right, clear? Okay, so that's the first question, and then the second one, a matrix is decomposed using SVD as below. Then the absolute value of determinant of SS transpose. Okay, so this is S, right? And if you look at the definition, right? What are going to be these values? These values. If you look at the singular value decomposition, that one, right? So these are what are those values? Eigenvalues, right? Eigenvalues of what? Eigenvalues of not S, it's going to be eigenvalues of SS transpose. Okay, so which means that the determinant of SS transpose is going to be 3.8287 multiplied by 1.6607 multiplied by 1.258. Okay, so that's a question number 2. And then if we move on to third one, they're asking for this consider matrix A equals to e power I theta plus e power minus I theta by 2, e power minus I theta, e power theta, e power I theta minus of. Okay. So here, we have this e power I theta. Okay. So for the let's just decompose this. Okay. What is e power I theta? E power I theta is cos theta plus sin theta. Am I correct? Which means that e power minus I theta is going to be equals to cos theta, because cos of minus theta is going to be cos theta again, minus, it's not going to be plus now, it's going to be minus I sin theta. Okay. So if you look at e power I theta plus e power minus I theta divided by 2, it's going to be equals to, these two are going to get cancelled, 2 cos theta divided by 2, which is going to be equals to cos theta. Okay. And then e power I theta minus e power minus I theta divided by 2, it's going to be equals to, now this cos theta is going to get cancelled, and then this is going to be 2 I 2 sin theta divided by 2, which is going to give I sin theta. Okay. So if you look at it, one value of the diagonal is going to be cos theta, and then other value of the diagonal it's going to be I sin theta. Okay. So
sir, in the denominator I is there, so I and I will cancel out.
what? Okay, yeah, okay. So this is going to be equal to sin theta, then e power minus I theta, then that's going to be, if you look at the other two values, right? That is so this is going to be cos theta, sin theta, cos theta plus sin theta, I sin theta, and then cos theta minus I sin theta, right? So for Hermitian, what should be the case? A should be equal to A. A should be equal to A star, right? Am I right? So which is nothing but A conjugate transpose. Okay. So if you look at it, the conjugate transpose of cos theta plus I sin theta is cos theta minus I sin theta, which is equal to this value. Okay. So this is a Hermitian. Okay. This is a Hermitian. We did not put some value of theta. Without even considering any value of theta, we were able to conclude that this is Hermitian, right? So basically, this will be Hermitian for any value of theta. Okay. Yeah. The trick is to write e power I theta to sin theta, sin and cos. The only way is that we should be trying to convert it to the values to something we know, right? Correct? If we just have the e power I theta and plus e power minus I theta, you might not know what to do with it. Okay. So that's why, since you know e power I theta is cos theta plus I sin theta, we just substitute it and then see it, then what do we get? Okay. So basically we're trying to convert it to something we know, so that we can better judge it. Okay. Yeah. Okay, we move on to the revision now. This conjugate transpose is same as the transpose conjugate. Okay. It's like you wear shirt and pant. You wear shirt first and pant next, or pant next. Pant first and shirt next, both the same. Okay. As long as you do both. Okay. So we'll just quickly go through the concepts. First thing, right? If you have followed until week 4, right? Week 4 and week 5 are actually two parallel lines kind of thing. They are like similar. Okay. The only difference is that week 4 with this the real values, and then here we deal with the complex numbers. Okay, complex numbers and complex matrices. Okay. So the complex matrix is just the counterpart of this real matrix, okay? Real vector of dimension. So here what we have is each number, right? Each number is going to be a complex number. Okay, you want me to discuss critical concept? All right. So one critical concept here to notice is that A plus IB, right? For A plus IB, I mean the way you define complex number is A plus IB, where this B is the imaginary part and A is the real part. Okay, you can represent that, that in the real name. Okay, so the real part goes in the x-axis, and the imaginary part B will be going in the y-axis. Okay, and since it make angle theta, okay, you could consider this distance to this point A plus IB, right? That can be considered as r. Okay, and then this theta, the angle with which it makes with the x-axis, right? That is the real axis. That is considered as this angle theta. Okay, which represents a complex number. So re power I theta is another way of like representing A plus IB. Okay, the complex number. Okay. So the linear combination of complex numbers can be done. I mean, where x is a vector, the linear combination of complex vectors can be done just like we do for the real vectors combination, right? The only difference is that here the constant which you multiply, right? In the real, in the real vectors linear combination, there it will be a real number. Here it could be a complex number, which basically means this complex number with which we are multiplying to the vector, right? That could be again complex. Okay, that could be of the form A plus IB again. Okay, so the inner product, is another important concept. So the inner product is defined as x dot y, right? In the inner product of two vectors x dot y, it's given as this x star y. Okay, x star is nothing but this x conjugate transpose. Okay, clear? X dot y is equals to x conjugate transpose or x transpose conjugate y, which is going to be equivalent to this one. Okay. Okay, we'll move forward. So since we have this x1 conjugate multiplied by y1 plus xn conjugate multiplied by y1, that's x dot y, right? If you do the opposite of it, y dot x, it will be equals to x1 multiplied by y1 conjugate plus x2 multiplied by y2 conjugate plus and so on, xn multiplied by yn conjugate, right? That is why you have this x dot y equals to y dot x. I mean conjugate of y dot x. Okay. All right. So basically, when we have this, when x dot if I'm multiplying the complex vector, inner product of complex vector with itself, right? Then it's going to be equal, because x dot x, it's going to be a real value. It won't be. It won't consist of the imaginary part. So that's why x dot y is going to be equals to x dot x is going to be equals to x dot x conjugate also. Okay. Okay. The other important concept is we forgot to discuss about this conjugate one. The conjugate for a complex number a plus ib is a minus ib. Okay. You just change the sign of the complex part. Okay, that is going to be the conjugate of it. So this is like the same value, the same radius r, but then with the angle of minus theta. Okay, this is going to be the complex conjugate, re power minus I theta. Re power minus I theta, as we have seen before, we expanded, it's going to be equals to cos theta minus I sin theta. The minus, it represents that we are having the negative imaginary value. Okay, so that is the inner product, and then so this A star is just A conjugate transpose. It is just it is simpler way of like representing it, because we use this A conjugate transpose conjugate like multiple times, right? They just represent it as like A star, and A star whole star is going to be equals to A. Okay, and then AB whole star, it's similar to this AB transpose one, it's going to be equals to B star A star. Okay. This we have discussed. We have mentioned that x dot y is equals to x conjugate transpose y. X conjugate transpose is nothing but x star. Okay. We haven't done anything new here. It is just a different way of like representing it. Okay. So, and the next important concept here will be this Hermitian matrices. If you want me to explain a particular part, right, or if you want, if I'm going too fast, please stop me and I'll explain that part again. Okay. Okay. So we have here Hermitian matrices are actually the counterpart of this symmetric matrices. Okay. What is symmetric matrix in the real space is nothing but the Hermitian matrix in the complex space. Okay. For a matrix to be Hermitian, it should be A star should be equals to A, which is nothing but A conjugate transpose should be equals to A. Okay. When we mean that A conjugate transpose equals to A, okay. Yes, discuss this part alone because it's important. You're saying that A equals to A star, right? Which basically means A equals to A conjugate transpose or A transpose conjugate. Okay. Let's consider this A transpose conjugate. Okay. Which basically means Aij, or you can just consider as like Cij because we're dealing with the complex numbers. Which basically means Cij, the transpose, right? In the transpose, this should be equal to Cji, right? Since we are doing the same transpose, and then we have the conjugate here. So which basically means Cij should be equal to Cji conjugate. Okay. For what about the case of I equals to j? Okay. Cii should be equals to Cii conjugate, right? Which basically means generally complex number will be of the form A plus Ib, right? And then the conjugate of it, it's going to be equals to A minus Ib. We are saying that Cii equals to Cii conjugate, which basically means A plus Ib should be equals to A minus Ib. Okay. Which basically means B should be equal to 0. Okay. Cii represents the diagonal elements, right? I mean C00, C11, C22, C33 and all. Okay. It's don't consider 0, consider it as 1. Okay. This is like we don't use 0 indexing, we just use the 1 index here. So C11, C22, C33, these are the diagonal elements, right? Okay. So for those diagonal elements, the B value is 0, which basically means the diagonal elements in a Hermitian matrix should be real. Okay. Diagonal elements are real. Okay. If this condition is not satisfied, then that particular matrix is not Hermitian. Okay. Along with this, we should be having this for others, right? It should be Cij should be equal to Cji conjugate. Okay. Okay. So we have few important properties for this Hermitian matrix. That is that all the eigenvalues of a Hermitian matrix, they are real. Okay, that is the first property. We will not get into the derivative part now, but then that holds true for all Hermitian matrices. Okay, and then the other important thing is that the eigenvectors corresponding to different eigenvalues are orthogonal. Okay, so suppose let's say we have this Ax equals to lambda 1x and then like Ay equals lambda 2y. When lambda 1 not equals to lambda 2, x is orthogonal to y, right? When we say like orthogonal to y, what does that mean? X dot y should be equal to 0, right? The inner product of both the vectors, it should be equal to 0. Okay. This inner product is similar to the dot product which we see in the with respect to the real vectors. Okay. All right. Until now, is it clear?
Yes, sir.
Okay. So this is to proof for it, and then yeah, this part we'll look at the later. Okay, the similar part for this Hermitian matrix is real symmetric matrix, and even for symmetric matrices for distinct eigenvalues, we have the corresponding eigenvectors are orthogonal. Okay, for symmetric matrices. When we have this Hermitian matrix, right, it is diagonalizable. Okay, which basically means we could be converting it to this form. We'll discuss about this diagonalization of Hermitian matrix in a bit. Before we discuss about diagonalization of Hermitian matrices, right? The other important concept is unitary matrices. Unitary matrices is like the counterpart of this orthogonal matrix, right? Orthogonal matrix which you see in the real space. What is the definition for orthogonal matrix? A multiplied by A transpose equals to I, right? Clear? So, which is basically means A transpose is nothing but A inverse. Correct?
Yes. Yes.
So could you explain orthonormal columns?
Yeah, it has orthonormal columns. Yeah, we'll discuss that in a bit. What we mean by this orthonormal columns, okay? We can even like do the proof for it. That's just like one line, okay? So we have this Q. I mean, similarly for orthogonal, right? Like we have Q transpose Q equals to I. The similar one is unitary matrices for complex numbers. Okay. Here what we have is the U inverse should be equals to U star, or in other words, U star U should be equals to I. Okay. U star U should be equals to I. What does that mean? When we have this U star U equals to I, right? Let's say I have the vectors A, B, C, so on something. Okay, this is equals to U. What's going to be U? A conjugate, B conjugate, C conjugate, and so on, right? This is going to be U star, right? This is clear? Is this clear? U star one?
No, sir, this is not clear.
This is not clear. Okay. So what is U star? U transpose conjugate?
Yeah.
Right? What is the transpose of this? What is U
Transpose.
transpose? Columns will become rows, right?
Yeah.
So basically it will become something like this. Right?
Yes. Yes. And taking conjugate of that.
Yeah, and then we take the conjugate of it, which means we do the conjugate for each other.
Yeah,
Okay?
fine.
Right? So when we have this, when we multiply this U star with U, which basically means we are doing this. So on multiplied by A, B, C, D, so on, right? So what will be the first element for this one? Can someone tell me? First element. How do you do matrix multiplication? You multiply row of the first matrix with this
Column
this.
with the, yeah.
Yeah. So basically, if you multiply this entire row with this entire column, that's going to give you the first element, right?
Yeah.
So this is going to be A conjugate multiplied by A, right? What's
A
going to be?
conjugate A plus B conjugate B plus C conjugate C.
Yes, A conjugate B plus A conjugate C. No, it's not going to be plus. I mean, basically this entire thing, right? While we're multiplying it.
Okay, got it. Yeah.
Okay, this is going to be A conjugate multiplied by A. This entire vector multiplied by this vector. Okay, so we have this A conjugate D and so on. Here we have this B conjugate A. Okay, this is going to be B conjugate B. This is going to be B conjugate C. B conjugate D. Similarly, we have similar vector. At the end, it will be something like N conjugate N something like that. Okay. And what we are trying to say is, for this to be unitary, this should be equals to I, right? What is I? I is identity matrix, right?
Yeah.
Right. So this should be equals to what? 1, 0.
Only diagonal should be 1 and plus 0.
Right? 0, 1. Right? Something and so on. It's going to be 0, 0, 0, 0, and so on, right? It's going to be something like this. So what's this going to mean?
Okay.
This is equals to 1, right?
Mhm.
This is equal to 0. I mean, if these two vectors are not equal, it should be equal to 0. If these two vectors are equal, then it will be equal to 1, right?
Okay.
Right. So what does this mean? This is similar to this A dot E, right?
A conjugate.
Right. Yeah. A dot E equals to 1. What does that say? The inner product is equals to 1.
Yeah, dot product of.
Yeah. Dot product of it is equals to 1. It means that the length of this vector is equals to 1, right?
Yeah.
Or to normal vector. Okay. And then all these vectors, right? I mean, all the vectors A, B, C, their length is equals to 1. Okay. And then we have this A dot B equals 0, A dot C equals 0, A dot D equals 0. Basically, any vector Ai, Aj is equal to 0 when I not equal to J. Okay.
Got it.
I mean,
Yeah.
if you consider this AI as a vectors of this matrix. Okay. For a unitary matrix, this one is like holds true. Okay.
Mhm. Yeah, this will be called as an orthonormal case vector.
Yeah. I mean, the same thing holds true for the orthogonal matrices. Okay. All right.
Yeah, fine.
Okay.
I think the first one in this example, first one is not unitary.
First one is what?
Not unitary. I solved it and checked. I think it is coming up as 1.
Which
Not
is
this one. The example.
Okay. This one. It is unitary. You're saying
Yeah, the first example that.
1 by root 2 I by root 2. This one.
Yeah.
Okay. Is it coming as unitary?
It's not unitary, I think.
It's not unitary. Okay, we'll check it. One thing is that the length of this vector is 1, right? The length of this vector is also 1. Okay? So the first condition is satisfied. The length of each vector should be equal to 1. Second thing is you should check whether these two are orthogonal to each other, right?
Okay.
So let's check that. It's 1 by root 2 I by root 2 I by root 2 1 by root 2. Right?
Okay, fine.
So it should be 1 by root 2 minus I by root 2 because we are doing the conjugate. Okay. Multiplied by I by root 2 and then 1 by root 2. Correct? This is A conjugate transpose. Okay. Multiplied by B. Okay. So if you do this, 1 by root 2 multiplied by I by root 2, it's going to be equals to I by 2.
1 by, yeah, I by.
Minus I by 2, it's going to be equal to 0. It is unitary.
0.
Yeah, it's unitary. Basically, they both are perpendicular, so it's unitary. Okay.
Okay, sir.
So the properties for this is for the unitary matrices, if you multiply a vector to unitary matrix, right? If you multiply a vector to unitary matrix, its length will not be changed. I mean, overall, it could be like rotated. The values could be changed. Okay, the individual values could be changed, but then the overall length of the particular vector, it's not going to get changed. Okay, that is one thing. And then you could see that. I mean, this is the proof for it. You need not worry about that. And then the eigenvalues of unitary matrix is always going to be absolute value of the eigenvalues. It's always going to be equals to 1. Okay, which basically means the modulus of lambda, right, or the eigenvalue, it's always going to be equals to 1. Okay, the proof for it you could see here. What's going to be the using the first one, we could do the proof for it. We have seen that ux is going to be equals to modulus of x, right? Right. So what if this is for eigenvector ux will be equal to lambda x, right? This is the definition for the eigenvector, right? So we have said that modulus of ux is going to be equal to modulus of x, right? Which basically means this should be equal to modulus of lambda multiplied by modulus of x, right? Which means this modulus of lambda equals to 1. Okay. The absolute value of eigenvalues is going to be 1. All the eigenvalues, absolute value is 1. Okay. Here also we have this, the eigenvectors corresponding to different eigenvalues of a unitary matrix are still going to be orthogonal. Okay, just like the Hermitian matrices. So, and then the other important thing is that we can have a Hermitian matrix A such that A is going to be equals to U diagonal matrix. This symbol is used for this diagonal matrix representation. Okay, U diagonal matrix multiplied by U star. Okay, where U is a unitary matrix, A should be A is a Hermitian matrix. So basically, we can decompose. We can decompose this A to this form. Okay, we can do the diagonalization of. This is called the diagonalization of Hermitian matrix. Now we have the proof for it. We'll look at it. Okay. So for a Hermitian matrix, we know that A should be equals to A star. Okay, and unitary matrix U star U should be equals to I. This is what we have seen from the previous from the previous presentations. We know that. What we will do is we just show for any matrix A, U equals to A can be written as U T U star. Okay, where T is upper triangular matrix, and then we show if A is a Hermitian matrix, then this upper triangular matrix will be a diagonal matrix. Okay, we just show that. If you just show this proof, the other proof will be pretty much easy. So this is Schur's theorem. That is like this A equals to U to U star. That is the Schur's theorem. What it basically says is you can convert any matrix A, enclosure matrix, right, to this upper triangular matrix form. Okay, where you use some unitary matrix. Okay, so we can do the proof for n equals to 3. That is this 3 cross 3 matrix. Okay, and that will be applicable for everything. So we will not look at the proof here. We know that the Schur's theorem states that any enclosure matrix A, right, is similar to upper triangular matrix where there exists a unitary matrix such that A equals to U T U star. Okay, U is this unitary matrix, T is upper triangular matrix. Okay. You guys know what upper triangular matrix is, right? Right? Do you know what upper triangular matrix is?
Yes, sir.
So for this is a proof for that, and then for a special case of our Hermitian matrix, right? It's going to be such that this T upper triangular matrix, it's going to be diagonal matrix. Okay, this is just the proof for it. Okay, we'll not get into this. Yeah, that basically discusses the entire part of the week 5. Don't think we have missed out on anything. Yeah. Any questions so far in week 5?
No, sir.
Okay. So what we'll do is we'll take 5 minutes break and then we'll continue with the next week.
Okay, sir.
Okay, so we shall begin again. Now we'll discuss the week 8. So one should ask how to get the process to get the upper triangle matrix. I hope you're asking about the upper triangle matrix which you talked about in the Schur's theorem, right? Sherry? If you're talking about this Hermitian matrix, right? Then the diagonal matrix, right? It won't be upper triangle matrix. It's going to be diagonal matrix, right? And the values at the diagonal, that's going to be equal to the diagonal value. The eigenvalues. So, but if it's like any n-cross-n matrix, then there's going to be some lengthy process to get there. But then we could actually do it. Okay? So we want to week 8 now.
So regarding this diagonal matrix, if you could show an example that would help us, because it's like
The diagonalization.
yeah, because diagonalization thing, because seems a bit difficult to us, and if you could let us know that what kind of questions could be expected on that.
Okay. If you're talking about just this diagonal matrix, diagonal matrix for this Hermitian, right? Then that's going to be easy. Okay? That's not complicated. You see that. Let's say we have A is a Hermitian matrix. Okay? So we have this A equals to U star, right? So this U, it's going to be the eigenvectors. Okay. Eigenvectors corresponding to this A. Suppose let's say we have this eigenvectors x1 to xn, so it's going to be equal to x1, x2, xn. Okay. This is going to be the corresponding eigenvalues. Lambda 0, 0. This one is going to be equal to lambda n. This is going to be the conjugate of it. I'm writing about the U star here. So the questions which you could expect from this is we would have actually seen it from the practice assignment and the grade assignments too. What we'll do is we just give you the C, okay, and then we'll ask you to find out about the select which are the following will be the correct diagonalization. Okay. So basically, if you know this eigenvectors, right, and then if you know the eigenvalues, then you'll be able to select the correct option. Okay. Clear? Is that okay? Is this okay, or like do you want something else?
Yes, sir, it's fine.
Look at this week 8 now. So what primarily we have in week 8 is simple. Okay, we have this. So what we do basically in machine learning now, or like in any other thing, right? We kind of like want to find the minimum or like maximum. Basically, like we want to kind of like optimize optimize a given function. Okay, basically we want to minimize let's say cost to the company. Okay, we want to minimize that. So we sometimes want to maximize the profit to a company. Okay, so we want to optimize certain things in our day-to-day life. Okay, this is like, I mean, these kind of problems we know. Okay, these are like they throw it up. So when it comes to like we'll see exactly like mathematically how to solve those problems. Okay, so we won't look at like I just give you the brief examples. I won't get into these examples. So in general, what we have is we have a function, okay, which is dependent on these variables, okay, or parameters. Okay, it could be this is an objective function which you want to minimize. Okay, f of x, this overall f of x value we need to be minimizing. Okay, and this what does this function? It depends on this x, right? Okay, this x could be a single variable, or it could be a vector too. Okay, vector of like d dimensions. So this is what we want to minimize it. So while minimizing it, we might be having some constraints. Constraints like, let's say if you want to find the maximum value for let's say minus x square plus 2x plus 1. Okay, for that you might be having some conditions of like x is greater than 0. Okay, or let's say x is less than 0, or x plus y equals to 1. Something like that will be having. Okay, so basically these are those are called as constraints. Okay, I mean, based on those constraints only we should be choosing the value of x. So these are called as constraints. Here we have two kinds of constraints, that is less than or equals to, greater than or equals to, those are called as inequality constraints, and then this equality constraint also put together. Okay, so the unconstrained optimization problem is basically like where we do not have this inequality or equality constraints. Okay, so for example, like if you look at this x minus 5 whole square, right? X minus 5 whole square, you want to minimize it. Okay, there's no restriction on the value of x. So the minimum value that is possible is, since it is a square, right? Square, it's always going to be positive. The minimum value that could be possible is only 0, and that will happen at x equals to 5. Okay, solution is this x equals to 5. So similarly, we have this. This is the objective function now for this particular example. We have this 3x power x, 3x power 6, 2x power 5, and so on something. Okay, we want to minimize it in the overall range of 4, which basically means it's unconstrained. Okay, the way you find the way you find this minima is this. Generally, we do this differentiation. We find the f dash of x and we equal it to 0. Okay, and then we solve for the values of x. Okay, when it will be minimum is when f dash of x should be equal to 0 and f double dash of x should be greater than 0. Okay, when you have let's say here this is like 5th degree, right? Okay, so you could be having maximum of five roots. Okay, and then for each of those values you should be finding the f double dash of x. Okay, and you should be picking those x values where f double dash of x is greater than 0. Okay, f double dash of x is greater than 0, and you can substitute those values of x. Suppose let's say we got 5 roots. Okay, and among those 5 roots for this f dash of x equals 0, we got let's say 3 roots where f double dash of x is greater than 0. Okay, so we do not know which among them, which among these is the least value possible. So what we could do is we could just substitute these x values and then substitute this x value in this objective function and see which gives the least. Okay, so that will be the solution. Is that clear?
Yes, sir.
So what we are looked at there is like until now we equating into f dash of x equals 0, right? That is the direct solution. Okay. The through iterative process also we'll be getting to the solution. Okay. Sometimes what happens is solving for the f dash of x equals 0, right? It might not be straightforward and it could take lots of computational time. Okay. So we go for this iterative process even though it does not give the accurate result like equating to f dash of x equals 0 case, but then we still go for it because we'll be able to reach approximate solution with the less time. Okay, the computational power required will be less, so that is why we'll go for this. So for this, I mean, in this particular scenario, what we do is we choose an arbitrary x, and then from that particular x value, we try to move in the direction of of the exact solution. For example, look at this x minus 5 whole square, right? You do not know that x equals 5 solution. Okay, so what you could do, you could take some value of 9, 8 or something, or you could choose some 2 value, 1 value. Okay, or maybe by luckily you could have chosen 5 also. Okay, but then what happens here is, from that point you should be moving somewhere, right? That is, you should be moving towards the direction of actual solution, right? So suppose if you are at 2, you should be moving towards right. Okay, if you are at 8, you should be moving towards left, because 5 is the solution, x equals 5 solution. So the good direction to move, that will be given by this f dash of x. Okay, so if you equals minus f dash of x, you'll be moving in the correct direction. So that will be apparent here, because when you have this x is greater than 5, the d should be less than 0. Okay, and then if you look at the f dash of x, 2 into x minus 5, when 5 is greater than 0, 2 into x minus 5 is going to be greater than 0. Sorry, when x is greater than 5, 2 into x minus 5 is going to be greater than 0, which means minus f dash of x is less than 0. So overall, this xt plus 1 equals to xt plus d. Since this d is like less than 0, we'll be moving towards 5. So basically, we'll be moving towards left from 8. Okay, and similarly, when you have this x is like less than 5, okay, when x is less than 5, this f dash of x is going to be f dash of x is going to be less than 0, and d equals to minus f dash of x is going to be greater than 0. So which basically means you'll move towards the right. Suppose if you're at 2, right, you'll move towards right because minus f dash of x is greater than 0. Okay, so irrespective of what the value of x is, if you choose d equals to minus f dash of x, okay, you will be moved towards the correct direction. Okay, right. So then what happens is, sometimes if we directly choose this minus f dash of x for this particular case of this x minus 5 whole square, right? What happened here is, if you choose a value of 10, you'll be going to 0, and then from 0 you'll be going to 10, 10 to 0, 0 to 10. We'll always like keep moving between these two. Okay, no matter how many iterations you do, we should be ending up with x equals 5, but that is not happening. Okay, so the other important thing is, it's not just the direction that is important, but the amount you are moving in that particular direction is also important. Okay, so that part we'll look at now. Okay, so instead of moving like directly f dash of x, we move a step direction. Okay, so that is like we move only the fraction of it. Okay, so that is called the step size. And what should be the step size? One should not be the step size, because previously we had chosen it as 1. Okay, and then we were like kept on oscillating. So if you take it as like, let's say 1 by 2 power t, okay, that is like where t is at tth iteration. What's going to happen is, you might not actually end up at solution. Okay, because after each iteration, the step size is going to reduce like drastically. Okay, so since the sum of the step sizes, it is going to be it's not going to be equal to infinite. That is just 1 plus half plus 1 by 4 plus 1 by 8. It's not going to be equal to infinite. It is going to be some fixed value. Okay, a by 1 minus r is going to be equal to 2. So 1 by 2 power t is not a good step size. Okay, so if you choose this 1 by t plus 1, that's going to be a good step size. Okay, clear? So 1 by 2, I mean, like, it should not be reducing it like too much. So 1 by 2 power t is not a good step size. You can choose this 1 by t plus 1 as a step size. Okay, So if you look at this, if you substitute this, so eta t as 1 by t plus 1, what you get is, you get xt plus 1 equals to xt minus 1 by t plus 1 into f dash of xt. Okay. When eta t, that is a step size, equals to 1 by t plus 1, then that particular algorithm is called as this gradient descent algorithm. Okay. So until now, what we looked at is, we took some arbitrary x value, and then from that after some iterations, we're trying to get to the minimum value. Okay. So what's going to, when will you stop? We have this xt plus 1 equals to xt minus eta into f dash of x, right? We are going to stop when this value equals 0, right? Because xt plus 1 is going to be equal to xt. From there, we cannot move anywhere. Okay? Which basically means that is solution. When will this be equal to 0? Eta t will never be equal to 0. So f dash of x should be equal to 0. So basically, when f dash of x equals 0, our algorithm will stop. Okay? So, but what does this f dash of x equals 0 give? It gives us the local minimum. Okay. So what could happen is, like I told for the example of this of the equation of degree 6, right? The f dash of x, it is of degree 5. Okay, even though f dash of x equals 0, it might not be the global minimum. It could be the local minimum. Okay, so for example, if you look at the graph here, okay, we have the local minimums, that is like within this region, within this small region, right? This blue color point, it is a minimum. Okay, so suppose if you start somewhere around here, right, to the left of this blue color point, you'll end up at blue colored point. Okay, but if you look at the overall graph of this function, this red colored point here, that is the global minimum. Okay, so this is also a minimum, but this is not the minimum for the entire range, so, or for the entire domain of x. Okay, so this is just a local minima. Similarly, we could be having so many different local minima, right? We have a local minima here, we have a local minima here, as well as here also we have a local minima. That is not mentioned, but we do have. Okay, so what's going to happen is, our gradient descent algorithm, it's going to give you one of these blue colored points or this red colored point. Okay, you definitely do not know whether you'll be ending up at the global minima or not. You'll end up at one of the local minima, but you do not know whether the local minima is global minima or not. Okay, so what should be happening is, if let's say for whatever we have the function, right? If all the local minima is also a global minima, then our gradient descent algorithm gives us the optimized value. Okay, because we know irrespective of like at what value we end up, right? We should be knowing that for those value it is the global minima also. For example, let's say for all these blue colored points, instead of having different y values, if you have the same y value, right? That is like this comes from, no matter which x value we end up with, it's always going to be the minimum. Okay, so if all the local minima is also a global minima, then that particular function is called convex function. So for that particular function, right, the gradient descent algorithm works well. Okay, because gradient descent algorithm gives the local minima, and for this particular case of convex function, the local minima is also global. So it works well. Okay. So the reason why we have this p as this minus f dash f x is, look at it here. The proof for it, the reason behind it comes from this Taylor series. So the Taylor series is nothing but the expansion for f of x plus eta d. That's going to be equal to f of x plus eta d f dash f x plus eta square d square by 2 f double dash f x plus and so on. Here, what does this say is, suppose let's say at a particular x value, I know the entire information. That is, I know f of x, I know f dash of x, I know f double dash of x, f triple dash of x, f 4 power, F fourth derivative x, fifth derivative, sixth derivative, I know all of it. Okay. What does that says is, right? If you know all of it, then basically you can get the function value at any other value, right? Suppose, let's say I know the f of 1, f of f dash of 1, f double dash of 1, right? Third derivative of 1, fourth derivative of 1, fifth derivative of 1, and so on. So if I know all of this, then basically I can get any f value. That is, I can get f of 2, f of 3, f of minus 1, f of 0, f of 1.5, f of 100, f of 1000. Basically, I could get any information. Okay. So if you know the entire local information at a particular point, it gives you the global information. Okay, it gives you global information at any point. That's what the Taylor series does. So using this, suppose hoping that eta d is like the step size is like very less, right? We could kind of like ignore this values, because if eta d itself is less, then eta square d square will be like very less. So if you ignore the higher order terms, we have this f of x plus eta d equals to f of x plus eta d f dash f x, right? From the Taylor series. Okay. Now f of x plus eta d minus f dash f x should be equals to eta d f dash f x. Okay. Now, okay. When we are looking for this optimization problem, right? What we want is we want to move in the good direction, right? What is good direction? The value of f of x should keep on decreasing, right? So which basically means f of x plus eta d should be less than f of x, right? Am I right? So for example, let me show you here. Okay. So here we are at this 8, right? We are at 8 here. So we want to move to move in the direction where the f value will decreases. That is, f of x value will decreases. So if you move to the left, right, the f of x value decreases. Suppose if you are at 2 here, right? If you move to the left now, the f of x will increase. But if you move to the right, the f of x value will decrease. So we always move in the direction where the f value will decrease. Okay. Is that clear? So that
Yes,
is
sir.
why what we want this f of x plus eta d to be less than f of x, right? Which basically means this eta d f dash of x should be less than 0, right? Then only this f of
Yes.
x plus eta d will be less than f of x, right? So that is the reason why we want this f dash of x. Okay. We want this to be less than 0. So we want to choose this particular d, right? We want to choose this particular d such that eta d f dash of x to be less than 0. Okay. But what if we choose ds minus f dash of x itself, right? So then this overall value is going to be equals to eta minus f dash of x into f dash of x, which is going to be minus f. You can even consider eta. Correct? So since we know eta is positive, we always know that minus since we know that eta is positive, then we know that when we substitute d as minus f dash of x, we know that eta minus f dash of x whole square is always less than 0. Okay. That is the reason why we choose d as minus f dash of x. All right. Until now, is it clear?
Yes, sir.
Okay. So right now what we have is we have this f of x1 comma x2, right? This is for, until now we looked at the functions where it depends on only one parameter x. It could be depending on so many parameters, right? x1, x2. This is for this is for the higher dimension, right? It depends on 2 parameters. Here we will not be having this derivative directly. We have something called gradient, right? Gradient, where we do this partial derivative. Okay. So initially what we had, we had xt plus 1 equals to xt minus eta into f dash of x, right? So here also we have the same thing. We have xt plus 1 equals to xt minus eta into gradient of f. Okay, gradient of f of x. And here x is going to be a vector. Okay, x is, in this particular case, x is going to be the vector which consists of two values, x1, x2. Okay, so it's going to be exactly like xt plus 1 will be equals to xt minus eta. Initially we had this f dash of x. Instead of that we have this gradient of f of x. Okay, which basically means in our particular example of x1 comma x2, this is going to be equals to x1 t plus 1, x2 t plus 1. Okay, it will be equals to x1 t, x2 t minus eta gradient. What does this gradient mean? Dou f by dou x1, dou f by dou x2 at x1 of t, comma x2 of t at x1 of t. Okay, is this clear? Maybe this
Yes, sir.
Yes, sir.
x1 of t plus 1, that might be confusing. Okay, we could, if we just take this as like AB, then it will be easier, I guess. Okay, so we take this AT plus 1, BT plus 1. Okay, consider, I mean, replace the entire equation which you saw previously. Think of that x1 as A and then x2 as B. Right? AT, BT minus eta dou f by dou A, dou f by dou B. Okay. At AT, I mean, which basically means at a vector x, xt equals. Okay, clear? This is for the higher dimensions. For higher dimensions, the gradient descent algorithm. Same thing. The same thing which I have explained. The gradient of f, it's going to be dou f by dou x1, dou f by dou x2. Okay. We'll not look at these examples because they're just like simple explanatory one. This is the gradient descent which I just mentioned. Xt plus 1 equals to xt minus eta del f of x or plus eta of minus del f of x. It's the same thing. The gradient, I mean the Taylor series, right? The Taylor series for higher order, it's going to be equals to f of x plus eta d equals to f of x plus eta d transpose del f of x. It's going to be d transpose because even though x plus eta d is a vector, f of x plus eta d it's going to be scalar. Okay, and f of x is going to be scalar. We know that gradient of f of x it's going to be a vector, right? And d is a vector. Okay, d is a vector. So we need to be having this as d transpose del f of x. So yeah, del f of x. Okay, clear? Is this clear? Why we are having this d transpose del f of x? Because d transpose del f of x gives us a scalar. Okay, this is similar to this having two vectors a b and then we do this a transpose b to get scalar. It's same thing. Okay, so why exactly this f dash of x, right? I mean, why exactly this minus f dash of x? We will look at it. So if you consider it as vector, right? Like we have seen there, right? When x plus eta d is a vector, that is x is vector, then d is going to be a vector and gradient of f of x it's going to be a vector, right? So what we should be having? We should be having this value, the left hand side as less than 0. So basically this D transpose del f of x should be less than 0, correct? Right?
Yes, sir.
So we have this, for us to get this D transpose del f of x to be less than 0, what does that mean? The dot product of these two vectors, D and del f of x should be less than 0, right? Am I right?
Yes, yes, yes.
Yeah. And when will two vectors dot product will be less than 0? Okay.
Below
Before we
the
get yeah.
below the line where like they become perpendicular. Right?
When they become perpendicular, it equals to 0. So,
Yeah, below that normal it will be.
Yeah, here this particular case.
Yeah,
same.
the whole region. Yeah.
Yeah. So how do you say that in terms of angle?
Sorry, sir.
Like let's say this is my vector, okay? And then like if a vector is here, right? D, right? This my W, let's say W vector, this my D vector. Okay. So if D vector is like making an angle 90 degree, then D dot
It will
W
be
will be
0.
okay. So you're saying that when I have it in like this region, right? It will be
Yes, it will be negative.
it will be negative, right? How do you
Yes.
say in terms of like, so in this direction, what will be the vector? These are the vectors, right, which are possible, right, in this direction.
Yeah.
In this region, basically. So if you look at it, what is the angles it is making with respect to this vector?
It is
It is
greater than 90.
Yeah.
Obtuse.
Right, up to that. So basically the angle between D and W, right? Angle between D comma W, if it's like greater than 90, then basically D transpose W or D dot W will be equal to 0. Okay. And if it is like less than 90, then it will be positive. Okay.
Positive.
So okay, now in place of W, let's imagine this gradient of f of x. Okay. You can choose any vector in this green colored region, right? It will still be less than it will still be negative. Why exactly choose this minus del f of x?
It will be the maximal value of all the negative values.
Yeah. So because the angle is like minus 180, since it is like exact opposite, it gives the steepest descent. Okay.
Yes.
That is the reason why we call the gradient descent algorithm as a steepest descent algorithm also. Okay.
Yes.
Yeah. So that's all from week 9. Sorry, week 8. So any other questions you could ask from week 8? No questions? So if there are no other questions, yeah.
Regarding this thing, right? Like earlier, we calculate the lambdas and right, like to identify about the definiteness and things like that for positive definite and
That
negative
comes
definite.
under this week 6, right?
Yeah.
The week 6 part that we discussed by Vishal sir in the next session. Regarding week 5 and week 8, if you have a question, sorry.
No.
That will discuss in next session.
Okay, sir.
Regarding week 5 and week 8, if you do not have any other questions, then we can use this session itself.
No, sir, that's clear.
Okay then. Thanks everyone. We'll close the session.
Thank you, sir.